All right, students, let me try another one here. This one I would put in that category of quantum mechanics and relativity. There are just some, I don't know if I should call it neat or weird properties that we didn't see in Newtonian physics. And so when you have this duality, when you can start thinking, and in this case, you can start thinking of the electrons as having wave properties, you can do things and build things and design things that you never really thought would be possible. You never even gave it much thought because you didn't understand that they had these properties. I mean, a good example is the electron microscope. I mean, if you think of them as just little particles, little BBs, and they can't, bounce off, they can't interfere with each other, you don't really see how you would use an electron to make an image. And yet we do that. We do that a lot. So the electron microscope is a very powerful and one of these tools that would only be even thought of when you start incorporating the duality. Anyways, there is just some weird things that it's hard to explain in quantum mechanics because there is no classical analogy. These are properties that if you try to explain it like, hey, this electron is a BB and blah, 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 you just can't do it. And one of those is what this problem is illustrating. This problem is illustrating that before quantum mechanics, we thought that if you had a particle, like a car, you could label, which is much detail as accuracy as you want to put into it, its position and its momentum. But we have what's called the uncertainty principle, the Heisenberg uncertainty principle. And it says that you can't know both of them at the same time. And maybe I won't repeat the whole lecture of this course, but it was this discussion about a wave. And something that has a well-defined wavelength means it repeats itself. And a well-defined wavelength, since wavelength has to do with momentum, Heisenberg reasoned that if you have something with a well-defined momentum and it continues on, you don't really know where does it begin and where does it end. And so there's a lot of uncertainty about its position. And so then he argued, well, then what if you had something that was waving kind of like that? So it starts here and ends here, so you know its position really well. Well, that can be thought of as a linear combination. You guys are probably learning this in your math class, a Fourier series of the wavelengths. And so you would look at this and say, well, wait, I don't know its wavelength really well, because to get something like that, it's really a sum of a bunch of waves with different wavelengths, one like this, and one like this, and one like this. You might even remember the fourth lab we did this semester was on the Fourier series and the Fourier analysis and on complex waves. We hadn't gotten to quantum mechanics yet, but if you got a moment, I would encourage you to go back and look at that fourth lab on complex waves, and that was the lesson we were trying to teach you here. Well, look at me. I said I wouldn't re-lecture on the uncertainty principle, and yet I really am. All right, so without deriving the uncertainty principle, and I'm not even sure the author derived it for you, you'll see that in later advanced courses, but Heisenberg reasoned out then, once you start looking at things as waves, and so that's, this uncertainty principle was true even before we started quantum mechanics. This was true for sound waves, it was true for water waves. Where do they begin and where do they end? It's kind of hard to define. And there's an uncertainty about them. And then that is also then true now if you're going to look at electrons with waves. And that's what's weird, because we would have never said that before this chapter. We would have said that, well, the only uncertainty about the position of a car or its momentum of the car, the uncertainty has to do with our lack of instrumentation, our lack of precision measuring it. And Heisenberg can say, no, there's just a fundamental physics. It doesn't matter how good your equipment is. Imagine, if you will, you have this infinitely awesome, perfect instrument for measuring the position of the electron. There's always going to be an uncertainty to it because it's a wave. And that uncertainty is then associated with its wavelength, and then that's going to have the uncertainty in momentum. And so this is the best you can ever do, even with the world's best equipment. So keep in mind sometimes the uncertainty principle gets misinterpreted as this is just a principle because, oh, we don't have enough technology to do these small little things. And that is not at all. This is just a fundamental property of the world. It's a fundamental property of all waves. And so it was true for sound waves and water waves even before we started quantum mechanics. But now if we're going to apply the duality to the electrons and they're treated as waves, then they have this uncertainty principle. Now, this problem illustrates that the reason we in the big world have a hard time understanding this is because that number there, Planck's constant, is so incredibly small that we almost feel like when we live in this big world that we can measure these with almost infinite accuracy. And most of the time, our accuracy is limited to the quality of our equipment and our technology, not limited to the nature. But this is telling us that even so, though someday we may get better and better equipment, we will never be able to measure them better than this. This is just a fundamental principle of the nature of waves. So this problem is trying to say, well, what if we lived in a different type of world? What if we lived in a world where h bar no longer equals this really small number, 6.63 times 10 to the minus 34, but h actually equals, and he writes here, 2 pi, which would be roughly 6.28. And so those are about the same. So if h was 1 times 10 to the 34 times bigger, we then would see the world around us in all of its quantum glory. Kind of reminds me of a fun book called Mr. Tompkins Mr. Tompkins Explores the Atom. And it's kind of a fun little story. So if you got any time during the summer, look up one of those old books. Professor Galmo would write these all the time. He's a fun writer, and he would imagine you getting smaller, and so you're the size of an atom. And that's what this one really is. You know, what if you're the size of the atom? You would actually see all these quantum effects, and it wouldn't be so weird to you, and everything would look kind of fuzzy. And that's why it says, suppose Fuzzy, which is a quantum mechanical duck, lives in a world where h equals 2 pi. So this fictitious world. Fuzzy has a mass of 2 kilograms and is initially known to be in the pond. And so what you would say is Fuzzy, and I'll just put the width of the pond. And so there's some water that is 1 meter wide. And so something that we can really understand a little better. And so you know the duct is somewhere in there, okay? So you make some kind of measurement. Maybe it's just as simple as you look and you see the duct. But as this is trying to point out, everything's going to look kind of fuzzy. So you don't really see a blob of a duck. You don't see a well-defined duck. You see a blob. You know Fuzzy is somewhere in the lake, though, okay? This goes on to say, then, what would that mean? And it says here, what is the minimum uncertainty in the component of the duct's velocity parallel to it? So in other words, if we know the position of Fuzzy to some degree, what we're saying is we don't know the momentum. So we see Fuzzy here, but then Fuzzy's got to be moving left or right. So let's work that out. The uncertainty then in the momentum would be mv, if we're not getting close to the speed of light. And the uncertainty in the position, I'm just going to put 1 meter. We know Fuzzy is not more than 1 meter. We know Fuzzy's somewhere in that lake. Okay, so that's the known. We don't know if Fuzzy's right in the middle of the lake or Fuzzy is to the left edge of the lake or the right edge of the lake or pond. It's not even that big. It's just 1 meter wide. But we don't really know where Fuzzy is. So the uncertainty is a whole meter. Fuzzy could be anywhere on that pond. And now that has to be greater than, or I suppose I should even say equal to, greater than or equal to this h, which is now 2 pi in this fictitious world, divided by 4 pi, which means we get, the pi's cancel and we're at 1 1/2. Okay? Or put another way, the uncertainty in the velocity then would be greater than or equal to, and I'd have my 1/2, and I'll bring the 1 over, and then I'll bring the other, the mass over, which is another 2 kilograms, and that's 1/4, which I'll write as 0.25. So what we're saying here is something that is trying to help you a little understand more about quantum mechanics. That, okay, we know at least at one instant that fuzzy's somewhere in here. The problem, though, is if fuzzy is there at that instant, there is an uncertainty of fuzzy's speed. So fuzzy is moving one way or the other, at least, maybe even, greater than, but at least at 1/4 of a meter per second. And so if fuzzy was definitely in the pond, there's a good chance fuzzy is not in the pond anymore, because that would be the uncertainty of it. And that's why B then comes into play. It says, okay, now, so assuming that this uncertainty in speed prevails for about 5 seconds. So 5 seconds later, where is fuzzy? So taking distance equals velocity times time, or maybe saying an additional unknown position now of fuzzy, is fuzzy's unknown speed of 1/4 of a meter per second for 5 seconds, giving me 1 1/4 meters. So fuzzy then, and so here's the whole point of this problem, is we know the accuracy of fuzzy. Sadly, or 1 meter, it's not even that accurate, but as time prevails, fuzzy's not even within that lake. And so fuzzy could have been on this edge moving that way and going out 1.25. I suppose fuzzy could have been at this edge also going 1.25. But we already incorporated that part of it. Fuzzy could have been at this edge of the lake and went 1 1/4. Fuzzy could have been in the middle and gone 1 1/4. Fuzzy could have been on the left end and gone 1 1/4. Okay. But what we don't really know then is where fuzzy is. So I guess I would say then that the fuzziness of it is an additional 1 1/4 with this edge. I guess it kind of depends on how you wanted to describe this. I probably shouldn't have drawn it 1 1/4 because 1 1/4 includes the plus or minus. So I should have gone half either way, but it could have been on the edge either way. So I would say probably the best way to answer this is now the unknown uncertainty would be the original 1 meter, and then I'm going to add another 1 1/4 meters to it to get 2 1/4 meters. So that motion is the whole idea. So we don't know fuzzy's position, but we also don't know fuzzy's motion. And so 5 seconds later, things are really getting blurry. All right. Hope that was somewhat helpful. Bye now.